Okay. May I start? I think no. There are still few. Let me just do this way. Well, I think that I can start and going through. So I have a lecture that actually was heavily changed. That is actually what I deliver at the Master in High Performance Computing on multi-core architecture and how to use them and best. We already know a lot of things about multi-core architecture, so I will go through this lecture very rapidly. And then we will spend time doing a little bit of exercises and examples on the real machine. So the agenda is this is the actual agenda of the lecture. So why multi-core was clearly explained by Luca this morning. A few issues that was already presented yesterday, and then the most important point is actually thread placement on multi-core and multiprocessor machine, because actually this morning Luca showed how to write a parallel code by means of OpenMP. OpenMP spawns different threads. How the threads, the way you can allocate threads on cores is actually quite important and depends on many different stuff, on many different considerations. We will discuss a little bit about that. There are tools to allow you. One is OpenMP approach. There are a lot of environment variables that you can use to specify which are the right way to place the threads the way you want. Then there are a couple of tools that I forgot to ask our sysadmin to install, hardware lock and NumaCTL, so we can actually play with liquid, that is actually a liquid pin that can do the same as well. And so we will play later in the exercise with a liquid pin. And then a lot of exercises. I have a tutorial and exercises to evaluate the performance of a multi-core architecture. Just because, I mean, it's important to have an idea what you can get out of the micro benchmark. Okay, just to be sure that your application, when you run your application, you are not too much disappointed by. Okay, because vendors tell you that the peak performance of the architecture is such a large amount of gigaflops, and then you try to run and you see that it's always still slow. Your application is still slow. So understanding a few things is important, and we can use stream as we did yesterday. We can use MPI. Well, this is a benchmark MPI just to measure latency among different cores. This is an exercise that maybe we can play also tomorrow. And then there is this not perf code coming from Intel that is actually show you if you write very efficient code because you know the machine, you can get really very much very good performance. I won't take, I mean, more than 30 minutes to go through all the slides. Then what we can do is do a little bit of exercise, and then after the break I have another small presentation about the libraries, optimized library, how to optimize your code by means of libraries. That relies again on the fact that we are using libraries that are multi-threaded library. Okay, so this was already discussed yesterday. Multiprocessor, more than one CPU, more than one socket. Here in the cluster that you have available is 2 socket or 4 socket. Each CPU is a multi-core. RAM memory is shared among all cores, as we saw yesterday. L1, L2 caches are private to cores. L3 caches is shared within the same CPU. The overall architecture is a NUM architecture, non-uniform memory access. You remember this. This is just a short recap. The motivation for multi-cores, I don't even read the slides because Luca, with all the information this morning, was actually quite clear in this. And this was already seen yesterday. What we have in a core, we have pipeline of arithmetic and functional units. So we have the pipelines, we have a superscalar processor, and we have a SIM extension, that is single instruction multiple data, that again Luca stressed this morning. Okay, so these are what we have into the core, in a core, and we have to use them efficiently in order to optimize for the core. These are peak performance, already discussed also yesterday, okay, clock speed, SIM factor, FMA factor, and superscalarity factor. That is actually instruction level parallelism, this one, no, because we can have more than an instruction at the same cycle. Luca also mentioned hyperthreading. Okay, let me just say something more on hyperthreading. So it's a technology provided by Intel, okay, that try to, I mean, it's actually a software technology, so you don't have actually two CPUs, but your operating system sees two CPUs, so you can schedule different instructions on different CPUs, okay? And the idea is actually that you always this way, you know, so you have a thread, if you have one single CPU, for sure you have some holes here in the flux of instruction, no? And so when you have dual physical CPU, you have this kind of stuff. You have a thread on one CPU and a thread on a second CPU, okay? And the idea here is actually to say, okay, due to the fact that we have these holes, if when this guy is not working, we can feed this guy with this instruction of a separate thread. So that's the point. So we can have a multi-thread on a single core, and there is some machinery, some software and hardware that allows you to split a single CPU from the logical point of view in two CPUs, with the hope that two threads on the same CPU can do this way and can actually maximize the overall effect of performance. This is quite complex to obtain in high-performance computing. It's actually quite nice and quite easy to see if one thread is, for instance, a web server serving a request. So somebody is asking some pages, and so maybe there is some hole, and this is not a database request. So if you have a web server and a database application running on the same CPU, maybe they can interleave nicely, and you can have a very good exploitation of hyperthreading. And this is actually something that Intel says that sometimes you can get, with hyperthreading enabled, you can get something like 170, I mean, your application, the overall benefit is in the order of 70% faster. So this means that you can combine the two threads in a right way without having all these holes. For high-performance computing is a little bit more complicated. Well, this is actually SMT, that's symmetrical multithreading. This is not an Intel technology, but is a IBM technology. Okay, and again, you can have this way in which you combine things and you try to be much more efficient this way. But the point is actually that the question is, does SMT-HT works for high-performance computing kernel? So hyperthreading actually just, this kind of technology just introduced an additional topology layer inside the core. So when we do liquid topology, we will see also an additional layer. So we have to be aware of that. Okay. Remember that caches and processor unit are shared. Okay. And so this means that there is a little bit more issues. Okay, I have a slide later that we can discuss further on that. But you can have possible advantages if you have, in the sense that a better pipeline throughput can be obtained, because in some way you can filling in another way the unused pipeline. This is a typical example. You have two threads running this way. You see, this is actually what Luca called a clear dependency. So you can't go very well here in a pipeline way, because to compute this you need the previous the previous guy. Okay, so at a certain point here, your pipeline is stalling. Okay, because you have to wait for this multiplication before completing this operation. So there is a dependency here. Okay, here you have also a dependency, but it's actually at a different stage, because to compute this you need 2 cycles before, no? Because this application, this multiplication requires -2. So it could be that this kind of threads can combine in an appropriate way. This could be the option. Okay, but if you don't have, if you don't have any dependency on that, and you have to execute these 2 threads on the same CPU at the same time, okay, hyperthreading is actually creating you a lot of troubles. Just because this goes straight on one thread, this goes straight on the other threads, and they are actually using the same ALU and the same instruction at the very same time. And so they are always compelling, and they are always conflicting for resources. And so sometimes we saw that hyperthreading is actually decreasing performance on well-written computational kernels, just because we don't have any dependency, and so we can't actually exploit this kind of stuff. And generally, the rule that we adopted so far is actually that when you have a node, a computational node that's required and that is needed for high performance computing, we just turn off hyperthreading. That's just because for the majority of the application, you don't really see a real benefit. I mean, the benefit could be of the order of 3%. That is nothing. I mean, we did some experiment a few years ago, and we didn't see anything. Actually, the majority of our applications were actually decreasing the performance in this. So our suggestion is still shut off or the disable hyperthreading, even if there are claiming. I saw recently a presentation done by people at CERN in which they say that with appropriate tricks, a little bit of hyperthreading can be useful, but still to be confirmed this. Okay, a multi-socket architecture 12 years ago was this way. We have 2 CPU or more than 2 CPUs. We have a node bridge, and we have a guy here that was called front side bus. Okay, and to the node bridge we had the RAM attached. Okay, nice architecture. This was actually an SMP architecture, symmetric multiprocessing. Because you see here that going from here to here, or going from here to here, it takes exactly the same time. Okay, this was actually a very good way to work, but you have a clear bottleneck here. Okay, because if 2 of these guys are actually using a lot of, if the 2 CPU are actually using a lot of the RAM, we are always sharing this front side bus. That's why that's why we moved from SMP to NUMA. Front side bus became rapidly a bottleneck, all the CPU accessing memory through it. And SMP UMA approach was no longer possible. The first NUMA architecture was provided not by Intel, but by AMD. That actually at that time, we are speaking about 2004, 2005. Okay, at that time, the CPU provided, the computational power of the AMD machine was much less than Intel. But due to the fact that the memory was no longer shared, that we don't have anymore the front side bus, so we have the so-called hypertransport technology, okay, make AMD actually the right choice to go for high performance computing. This was still true, this was true till 2009, when Intel came out with its own solution that is actually the quick path interconnect. So for 5 years, 6, 7 years, AMD was the right way to go. No way. Even if you go for peak performance of the CPU was much better Intel. The problem on the front side bus was actually dramatic. then, of course, this is actually the idea, no? That we saw yesterday. So we have 4 cores, so 4 sockets, sorry, and each socket has its own memory, private memory, okay, that is then shared by means of a certain number of links. This certain number of links is called hyperthreading, hypertransport for AMD. The same goes for Nehalem, okay, in which again you have the CPU attached to the memory. And Nehalem was actually, it's 10 years old because it was out in April 2009, but was actually the first appearance of QPI, so the Quick Path Interconnect, that now is no longer called the Quick Path Interconnect, but is called with another name, but the concept is the same. So we have CPUs, we have memory, and then we have something that connects the 2 CPU and the memory. So when I have to write from here to here, I go through the quick path. That is a sort of network within the CPU that connects the different sockets. Okay? And this is actually a modern CPU, Broadwell, that we have on the cluster that we are using. And you see that the situation, these have 22 cores, and the situation, each core is here, and this is actually the quick path that we have, okay? And so it's quite complicated, these 22 cores, these 14 cores, and these 8 cores. In any case, you see, there is always this link that links together the different cores within your CPU, okay, within your socket. And in this way, you get rid of the frontside bus problem, but still you can have trouble in performance, because we are now on a new architecture, non-uniform memory architecture. So ranging, going from memory from this guy or this guy is actually a completely different path. Okay, and so we have some challenges here that actually we need to rely on the exploitation of multiple thread parallelism. So we need to be sure that when we when we do parallel programming, we are sure that things that needs data from one memory are close to that particular memory, because actually we are actually aggravating the memory wall problem, because we have now not an uniform access to the memory. Okay. And then there is also the problem of the cache sharing, because we have memory bandwidth and also cache sharing. This slides was discussed in detail yesterday. I discussed it in detail yesterday, and I think the coherent link is actually QPI, or hypertransport for AMD. Okay, and so we have to be sure how to place things, and we have to be sure not to share too much, or to be sure that when we are sharing things, we are sharing things in the right way. And I think that, Luca, you discussed this quite nicely. So again, the same, this is a very stupid problem in which you just sum numbers, and if you split it into processor and you do a round robin mechanism, you have this way. So processor 1 does the even numbers, the processor 2 does the odd numbers, and you can check the topology about that. But then you can have, this is actually what is happening. Okay, you have to read B and C and rate A, processor 1 and processor 2, and the point is actually that when you read this guy, you read processor 1 and processor 2 start, well, it's not really clear that the color are quite similar here on the slide, on the screen on my slide are a little bit better, but you see that what is happening is actually that when you need something, processor 1 read the entire line, okay, and then do something, then processor 2 read again the entire line, because it's just one element away, and so you start actually reading the same cache line, and so the cache is actually invalidated because you can't modify this one when this is actually reading that. And so for the cache coherency protocol, you are always trashing your cache, and you are actually not using at all caches. Actually, you are slowing down your application by using cache in the completely wrong way. Okay, and so that's actually quite important. Here is actually, so processor 1 does this operation, write into the line containing A0. Okay, this marks the cache line containing A0 as dirty. Look, this is actually changed. And so if processor 2 is doing the same stuff, so it detects that this line is wrong, okay, and so get a fresh copy from processor 2, write into the line containing A1, and then this mark the cache line containing A0 as dirty, and at this point things are coming back. So they are always say, I'm actually changing my dirty, my line, and so there is always a cache trashing going on. I'm reading, I'm writing, this guy throw away the data, have to reload the data, does this operation. In the meantime, the other guy does the other operation, but finds that the cache line is dirty, so throw it away, read again, and so on and so forth. So you actually, it happens that you read and write your cache line more than one time, and so you are actually adding overhead to your application, and nothing is actually working the way you see. Yeah, exactly. So you just, this is dirty, okay? This is actually C that is wrong. It loads again, and then you have to redo the operation because it can't save its own data.
Can this bring to the so-called, it seems to me that yesterday you spoke about cache resonancy issue.
Exactly.
When we are
exactly. The cache is always, this is on, cache trashing or cache resonance are more or less the same concept, correct, Luca?
Sorry?
Cache trashing and cache resonance is actually more or less the same concept.
Yeah, they are related. Yeah, I have a couple of slides on that. Oh no. I heard that you're thinking.
Your two slides are always frightening the audience.
That could be an interesting.
Yeah, maybe.
It takes 1 minute.
Okay, in any case, this is actually what is happening and what you have to take care of. So to do that, the important point is how to know how to take threads and assign threads in the right way. Okay, so if data are here, thread 0 should go here and not should go there, and so on. So arrange things in the right way. Okay, and to do that, I mean, the reason why to do this should be clear now. We can eliminate performance variation, just because, again, if you measure the performance on a thread that is reading here, and then you measure again the program, the performance of your program that have threads that read data now here is actually far away, and so times are actually not consistent, and so it's complicated. Of course, this could be not so. The difference maybe is not you can't appreciate it, but I mean on quite complex code, this this effect sum up, and you can see quite striking differences in running in one way, and running in another way. Okay. So, and then of course, if you know how to place things, you can actually use the best architectural features. And of course, you can avoid resource contention. And the point is actually that you don't know exactly what to do, because the dilemma is here. Suppose that you have a very simple architecture. These are actually nodes available 5 years ago or 10 years ago. Just a single core with a single socket with two CPU with 2 cores. So one of the first multi-core architecture. In any case, here is actually the point, no? So should I use core 0 and core 1 because they share this cache, and so I can improve synchronization. In this way, I improve synchronization cost. Or should I use core 0 and core 2 and go for maximizing memory bandwidth? Okay, so That's a very, very good question. So it depends, of course. The answer is it depends, as always in high-performance computing. There is no single solution for all the problem. Each problem has its own solution, and it's complicated to define it. And it depends not just on the size of the problem, but on the machine that you're running the problem. In any case, it depends on the application structure and on the machine structure. So if you are doing a stream, it's much better to do this, one here and one here, because in this way you can exploit the two caches in a completely independent way, and you don't have any conflict here on this core. Okay, if you are interested just in CPU and not in memory, maybe having the two here and can share just L2, they can share just L2 and for a small amount of data, and so you don't have too much memory contention and RAM and cache contention or cache coherency problem here, if your problem does this. Of course, once you go on a different machine in which you have not this kind of architecture, things have to be rethought and have to be rechecked against the architecture that you have. Of course, to do this kind of operation, you need some tools. There are many possible ways. NumaCTL was actually the one that we used for a lot of time. Now we are starting using Liquid Pin, and we are also using hardware lock that I forgot to ask Michele to install on the cluster. So we will try to use Liquid Pin. Of course, these are tools that are just the tools that can be prefixed to your program, and we will play a little bit with Liquid Pin in a moment. Okay, and then of course you can also control all this kind of stuff by means of environment variable that OpenMP program is able to read. So you have OpenMP place, OpenMP proc bind, and KMP affinity that is actually quite related to the Intel environment. So thread placement with Liquid Pin. This is taken from the main page. You can see a little bit of information by Liquid Pin -H, and then you go for this is actually a typical way to do Liquid Pin -C 0, 2, 4, and 6. So you have 5 threads here. Okay, you place the first on core 0, the second on core 2, and then the other 3 on 4, 5, and 6. So in this way, you are pretty sure that they are there. Okay, and so there are some reason to do that. Okay, and you can do this way and see the changes in terms of performance of your application, and so then decide what to do. There are many different domains in terms of liquid, and you can see them with Liquid Pin -C, and you see that the first domain is in N, that is the number of cores that you have. So here is just a long list up to 71, from 0 to 71. I just cut out a little bit of numbers. This was done on your on the node I was this morning, C7 something. So it's a 72 cores, 72 core machine. Then you have the domain S, okay, and then you have also the domain M. You see, domain S, socket, CPU, and memory. Okay, so you have different domain, and then you can specify where you wanna put your application. Okay, and in this way you can actually play a little bit, and I can try to show you which kind of effect you can have in changing the places and asking which kind of stuff. For thread placement by means of OpenMP, you have this environment variable, and so can be the placement can be controlled by 2 environment variables. OMP proc bin describe how the threads are bound to the open places, and then OMP places describe these places in terms of the available hardware. You can play around with them, and if you use OMP display environment to true, you will see the way OpenMP is actually is actually printing out. This variable allows you to print out how the threads are placed by means of the choices that you do using these two variables. I have to say one thing, that if you use liquid pin actually override this kind of variables. Liquid pin also override the OMP num threads variable. So if you say liquid pin run on 12 cores, you run on 12 cores, I specify that, and you don't have the need to set this kind of variables. Okay? So this is actually a way the way OMP place works. For instance, you can say export OMP place equals sockets, and so you do this way. So you have, suppose that you have 2 sockets, each of them with 4 cores. If you do this, you say that thread 0 goes here, thread 1 goes there. So it's actually distributed this way, the socket, okay? So it interleave the threads among the two cores, okay? And this is the way it goes. If you say cores, it's completely different, because in this way you just force to have the threads assigned to the cores in this way. So C0 goes to T0 and so on. So you don't have any interleave, and all the cores goes this way. Okay? So if you want to do an OMP places equal cores by means of liquid, you just use the n and say 0.72 if you according to the number of cores that you have. Okay? And then you can do something like that. You can say threads, but then you say, OMP place equal cores, but then you set OMP prox bind spread, so you actually spread again things the way we did before, okay? And so you can combine this way. So this actually, what is the differences between these two? Because you see that when we did OMP place sockets, we had exactly the same behavior of these two variables. Here, well, the difference is that the latter choice does not bind the thread to a specific core. Okay, so the operating system can move the threads around. Okay, and and you can also put more than one thread on the same core, even if there is another core still unused. So in order to be sure that you want one core per thread in the right way in a interleaved way, go with that and not with that. Okay, and then there is the thread placement that is OpenMP affinity by means of Intel compiler. You have this environment variable KMP affinity that is quite complicated because you have many different modifiers, many different types. Okay, the default are written here in red, so you have you can specify find threads and core, no verbose and respect and so on. This is a situation, but it's quite flexible, and of course, if it is flexible, it's also a little bit complicated to play the right way. But this is actually the thing, the similar way you can do. You can do KMP affinity scatter. That again means I'm scattering my threads in a round robin way. Okay, and then I can say KMP affinity compact. Please put all my threads in the same socket in an order way. So different way, different kind of results that you can have. And then you can also be explicit, and you can say, okay, I have 8 threads, please put them using this processor list. And this actually can be done the same way in liquid pin, because you just mention which threads you want. Okay. The reason to do that, well, complicated. I mean, maybe you have a very particular application that is important that you have this way. And then KMP affinity no one, random placed by the operating system according to their to its kind of algorithm and according to the load of the machine and so on and so forth. Okay, hardware lock we don't have it, but I mean it's actually a nice tool that allows you to do a lot of stuff. It has two parts. You can set a set of command line tools, ls top, hardware lock bind, and so on, that actually more or less what you have available on Liquid. And then you have an application programming interface in C, in Python, and with Python and Perl binding as well, that allows you to do a lot of interesting stuff, because you can actually, by means of this API, you can actually code the way, you can actually ask to your code to place correctly the threads. Little bit cumbersome sometimes, but if you have a code that you know that it's always the same way it runs, and it runs forever on a cluster, you can also think to have it directly written into the code itself. So these are a few comments, but I don't want to go too much on this. So you can bind the process to a given set of CPU, and you can have this nice feature to bind the memory as well. So you can say hardware lock bind, memory bind on node 1, and then CPU bind on node 1, socket 0, and so you can see the effect of this. And then you can also distribute memory this way, in which you mem bind, and then you define which is the mem policy that is interleave all. That means that it interleave the memory accordingly to the architecture that you have. So that's more or less, I think, all. Yeah, the problem again in performance here is about this, is the cache coherency NUMA performance problem. The whole memory is obviously transparently accessible, so from this guy you can reach this memory without any trouble. The point is actually that if you place the memory here, and then your threads accessing these memories here, is not really a nice way to go, okay, because you have to travel too much. What you would like to do is actually that these threads access the memory on these banks, on this socket, and the same for this. So this is actually the ideal situation. So how can we make sure that memory access is always local and distributed as possible? So suppose that you have many different threads that read many different locations of memory. You would like ideally that these threads actually read the memory here, and the other threads read the memory here. So that's actually the main challenge, and you have to be sure that, and you have to be aware, but also this was actually discussed, well, we can is actually, let me go here, that by CCNUMA default memory location, the golden rule is actually that a memory page gets mapped into the local memory of the processor that first touch it. And touch doesn't mean write, not allocate. So it is enough to write a single element to map an entire page. So the point is actually here is actually that if we have this, okay, if you do this operation is not yet mapped, but if you do this at the first stuff, when you do the loop, your mapping takes place here. And so this means that it can happen that you write, if you do, let's just give you, if you do this operation, this is a very simple OMP program that already discussed. If you do this operation, that is the initialization, memory here is touched, okay? And so it could be placed due to the fact that this here, I mean, this is actually the Fortran 90 syntax. So this is an array, but if you do this, you initialize the array, so you are touching the memory. And if you initialize the array without any kind of parallelism, because this doesn't have any parallelism inside, and so it's actually touched directly on a single, on one processor, okay? So when you do this, that is a parallel region, threads can be on a different socket, okay, because maybe here you have a lot of different threads, okay, and at this point, you are accessing the memory from a different location. I don't know if it's clear, but the point is actually here, no? Again, let's have 4 cores here and 4 cores here, okay? Memory here, and memory here. Okay, and these are of course connected by the hypertransport. So this is RAM, and then this is a CPU. Okay, in this case, I'm initializing in a serial way. Okay, so what is happening is actually that my array A is stored here because this guy actually touched it, and so for this reason the memory is here. Okay. Then when I parallelize it, I can be quite efficient accessing this the first part of the array. Okay, but not at all efficient for the second part of the array. Okay. So what I have to keep in mind is that actually when I initialize my array, I explicitly initialize it in a parallel way as well. Okay, and so in this way, okay, I do a schedule static and I say, okay, perfect. At this point, I can parallelize my array in a way that half of the array is here and half of the array is here. And then when I access it, I'm accessing it without having any contention and reducing a lot the and having no contention and also the same speed for any section of the array. Okay, that's actually a trick that you have to keep in mind when you go for data locality. Okay, so that's actually all from my side in terms of slides. So this is actually a summary. In ubiquitous NUMA system, threads and process placement is a must. Of course, I mean, you have a lot of tools to do that, NUMA CTL or Liquid and hardware lock. You can play with the environment variable to do that. And if you play with Intel, that is actually highly recommended choices because Intel compiler is for is quite good in actually in optimizing the code. It's even too much good because sometimes it plays really dirty tricks if you are not careful about. But in any case, KMP is also another important tool. So yeah, and then we have a few examples and a few tests to play with. So what I would like to do now is here. Okay, are you able to? Well, maybe I can increase a little bit. So here I am on a node. So let's take a look at the topology. The -G is graphical topology, and without -G you see a little bit better because I mean the node is too large enough that you can't fill in. So we see here what is the situation. We already discussed this yesterday. 4 sockets, 18 core per socket, and 1 threads per node. This is the list of cores. This is the list of sockets. So, and this is the cache topology. So we have a size 1 that is for 1 core and so on. Size 2 that is again for 1 single core, and then we have a level 3 cache that is 25 megabytes, and it is actually in 4 different cache groups. And then we have the NUMA topology with the distances and the free memory and the total memory. Okay, great. So if we do a liquid pin -C, we see liquid pin -help. -P, not -C. Okay, so these are all the domain that I show on the slides. You see, you have the domain n that is actually the number of cores, then the 4 domain for the socket, the 4 domain for the core for the node, and then the 4 for the CPU, and then the 4 domain for the memory. Okay, and what we can do now is actually that this is actually an example in which we run a simple program. Well, I run, let me see, well, let's go this way. No, because let me just recompile the code. Yeah. I can compile my code here and calling it stream.omp intel.x. Okay, I'm compiling with Intel. So if I do an LD of stream OMP Intel, I see that this is actually an Intel, an OpenMP program, okay, because it actually needs this library, okay, and also needs the libpthreads library, okay. Do you know the LDD program that shows the dynamic library that your application needs? Okay, and so you see that this is a program. This is actually an OpenMP program, because otherwise, if you do this on stream, you see the difference. Stream was actually compiled without any QOpenMP command flag, sorry, and so this is actually quite serial program. It doesn't require no specific library, just use the standard C library, okay, and nothing more. When I compile the code in this way, okay, I have, well, of course, if I do the stream again, you see that now in this file, well, this is the difference. Sorry, I made a mistake, but it's interesting to show you this. Okay, so this one is the serial application. No way. This one was actually compiled with GCC. Okay, you see that I have GOMP library, that is a GNU library for OpenMP, okay, and again the libpthreads. Here I compile with Intel, and I see that I have the standard 2 library here, the Linux 2 library, okay. Then I have this libOMP, then I have libpthreads, and then I also have libGCC, that is another library that the Intel will link against. Okay, so same program, same source code, 3 different output, 3 different executable. Okay. Now what we can do is actually to say, okay, let's now run the code, the stream. Let's have the stream OMP X. This is actually the Intel, the GCC one. Okay, I run this way. Okay, it runs on 4 cores, just because I have OMP num threads set to 4, because probably I asked, I don't remember, I asked 4, and then I see these numbers. Okay. Then I can run the Intel one. And I see quite different numbers. You see? 27, 28, 36, 33 for GNU, and then this quite better. So our first conclusion is actually, well, let's use Intel. That is a quite good conclusion, because I mean Intel is actually better. But is due to the fact that Intel is much better in compiling this, or there is something different here? Well, probably it could be that Intel is actually able to scatter or to set the threads in the right way. So we can try to add, we can try to do this experiment. Okay, I can try to do liquid pin minus C 0 4 0 3 stream omp.x. Here I'm placing the 4 cores on the the four threads on the first 4 cores. Okay, I'm sharing a little bit of things here. Remember that the way I'm doing the experiment is actually that each core, actually each thread, will spawn its array, okay, and then read the array. Okay? Number actually decreased. Okay, so let's try now to put this on 0, the other one on 17, the first on the third on the what is the number, 17, 18, 35, correct?
It should be 18 to go to the next.
Correct, exactly, 18. Then we go to 36, and then we go to 50, help me, 57? No, 54, correct. Okay? So this means that they are actually on 4 different sockets. Let's see what's happening. Things are getting better, no? Just because, I mean, I'm actually splitting correctly my array and says this reads from here and this reads from here. Okay? And so I'm actually getting a little bit of performance. This actually can be done. Let's now try to do Intel. And let's ask Intel to do the C03. Okay? This again, I'm packing everything. I'm packing everything on the first socket. You see, things are. If I run this way without any suggestion, it's much better. Well, much better. Well, it's yeah, 10 gigabyte. Yeah, Intel works well with the cache, but there should be also some other mechanism here that Intel is actually understanding exactly the way to put the threads, and probably because the default of KMP is actually not. So maybe now we can actually play a little bit with the export KMP affinity, and we can say that is scatter. Okay. It's even better, because actually now I'm saying scatter means scatter in round robin, so the first on the first socket, and the second on the third on the second socket, and so on. And actually I'm getting 50 gigabyte per second. That is actually not exactly linear with respect to what we obtain on a single core. No, you remember yesterday that on a single core, well, we can run the stream benchmark in serial. Okay. And this actually runs in serial, so it reads from one core and reads on the memory. And you see, these are 15. But now when I run 4 of this guy, okay, in a scatter way, I'm getting almost 50 gigabytes per second of bandwidth. That is actually not so bad, actually. So, I mean, much better than the default one. So, knowing exactly where to placing the cores and the threads can improve your performance quite considerable. Of course, this is a very stupid, well, very stupid. This is actually a benchmark that measures performance in terms of memory bandwidth, okay? So here we are actually choosing the way that we would like to split our threads in a way that we maximize memory bandwidth. If you have a CPU intensive code, that could be not actually the case, because maybe it's better to keep the cores quite close on one CPU, on one socket, just because they have to communicate often. And at this point, it's not actually much better that to communicate within cores that within a socket that outside the socket. So it's actually this kind of reasoning that we can have. So I have then the exercise I propose to my student generally is this. Well, by the way, here actually have, you can disable and enable hyperthreading, and it would be really nice to see the differences in that. But this, I think, we need the permission by root to do that. And but in any case, that could be also something that you can play maybe on your laptop. Yeah. Yeah, the first exercise I was proposing is actually about a very stupid code, OpenP 101, that now has a different name, to understand correctly how to change the number of threads, but we know now OMP num threads is the variable to play with that. Then learn how to use hardware lock numactl liquid command, again with this small program. Exercise 1 is actually this one, that is actually to run stream benchmark to test different performance when wrongly assigned to processor. And the idea here is actually, that we would like, by means of numactl or by means of hardware lock, we are actually placing the RAM on one node, okay, and the threads, the computing part, on a node, socket, sorry. So we ask, instead of doing this way, we actually say, allocate the RAM here, okay, and then read from here. And you will see that stream gives you quite different performance on that, okay. And in this way, you can evaluate the cost in terms of stream, that in terms of memory, if you do the wrong allocation. Actually, I prepared the exercise was prepared by means of NUMA or hardware lock, and so we don't have the two tools. So no. The other point, I don't know if you are able, but I mean it's not strictly necessary. We can play this exercise tomorrow. The point is actually hardware lock. If you are HW lock, if you are able to. Sorry about that, but I forgot to. And then. Yeah, then this is actually a way to nodeperf.c is actually a code that comes from Intel cluster tools, written by Intel, and you can try to check which kind of performance you can get out of these tools on your node, okay? And this was taken from a book that I strongly recommend you, Optimizing High Performance Application with Intel Cluster Tool. And there are a lot of exercises. One of them was actually to play with this nodeperf command. Nodeperf program, sorry. So this is actually written by... so this actually is a right way. I mean, it's the right way. It does actually nothing but matrix-matrix multiplication. But it does it in the right way, so exploiting at maximum the hardware of the machine. Okay, so this is actually node perf. Of course, it tells me that I mean, again, if you do so, you see that it uses libmpi, and it uses also libmkl, matrix, the mathematical kernel library from Intel. You see, it doesn't find it because we have to load the module list, module avail. Ah, but you don't have MKL as module, correct? No. List. E perché allora non lo trovo? Export. That's the reason. Okay, let's see if we are able to compile the code here, just saying this. Michele, you see, this is actually the problem that we have yesterday, libfabric. So this is actually due to the fact that MPI ECC seems not correctly manageable. But let's try one more things. Module list, module purge, get rid of everything, module load this version, and then okay, for no, you don't have for 2018, you didn't modify the no. Okay, so the compilation requires a little bit of tricks to do that because we need the MPI, and the MPI is not available for Intel. Let me see if we are able to compile it for yeah, let's try it this way. Okay, now it's working the right way, but MKL root is not available. Ecco. Okay, so this should be in apps. Intel. Intel Parallel Studio. Can I run this? Ok, ecco. Perché non mi sorry, it's not able to find out the MKL libraries that are present on the system, but probably they are not configured the way I. In any case, I think that we can, due to the fact that we are discussing about mathematical kernel library that we will use to compile this code if we are able, and I have to try to fix it without losing too much time. What I would like to do is actually maybe I can anticipate the other presentation I would like to give you, okay, and then we can go for the break. During the break, I will fix a little bit the things, and then we can go for all the last session of exercises. Last section for exercises after the coffee break. So this is actually, yeah, this is the slide I plan to show you. So okay, so this is actually the agenda. A very short introduction about the optimization technique that we discuss, or we touch, briefly touch, and then how to use optimized library. Maybe I can start from this about the locality of reference. That is actually the most important point in terms of optimizing the memory, no? Because the memory hierarchy tries to exploit locality. Locality can be of three kind. It could be temporal locality. It means that I'm using a variable, and so it's actually quite there are chances that I use this variable after a very short time. So we would like to have this aspect of temporal locality. So recently referenced items are likely to be referenced again, and so I would like to keep them. And this is actually the idea, to have a working set concept, because I have a bunch of variables that I'm using very often in a while. So iterative loops, subroutine, and local variable. Then, of course, we have a spatial locality. That is actually what we discussed this morning when I show you the matrix-matrix multiplication aspect. Okay, it means that if I use an element, it's actually quite, it's likely that I'm using also the element close to this other, no? Especially for matrix and array and so on. So program access data which is near to each others. And these are all the operation on table arrays. And here the concept is about cache line size, okay? Because the cache line size is actually determined by the spatial locality. So I can read the cache line, okay, and then I fill in the data. And as we saw before, if the cache line, I store all the data in my cache line, and if I'm using the data one after the other, I can stay in cache. And this is actually why I can speed up my code this way, okay? And if you are in this condition, you can really exploit. So this actually you exploit the cache mechanism. And this is actually spatial locality. Then you have sequential locality, that is actually the concept of that Luca mentioned. Is actually if you are writing your code and your instruction set in the right way, I mean, due to the fact that you have to load from the cache, also you have to load from the memory also the instruction that you have to perform. Okay, if you have all the instruction, if you write your code in a way that all the instructions are quite close to each other, you can actually avoid these branches in other places, and then you can exploit also the cache from the point of view of the instruction. And remember that on L1, that is very small, L1 is always split. There is L1I, that is L1 for instruction, and L1D, that is L1 for data. So they are split this way. Okay, so locality of reference is actually quite important. I mentioned yesterday this about user system and wall time. That is actually a way to check what's going on your system. Real time is the total time elapsed from the start to the end of the time and task. CPU user time is the time spent executed in user space, and it does not include the time spent in operating system calls. And then the CPU system time is the time spent by the system itself to do operation on your code. Okay. Generally, what you see, well, this is always true. CPU user time plus CPU system time is less than real time. And then you can have the CPU percentage spent on the process that is actually generally equal to 1% plus user time plus system time divided by real. And yesterday, by means of top, we saw this number. And generally, a good high-performance computing application should see always the top is around 99% or 100%. Okay? Because actually this means that you don't spend time in system time. Okay? If you see a large fraction of system time, it means that your application is actually have some trouble, because I mean it means that there is something that happening on the machine or on your application that requires a lot of system time, and this could be quite a symptom of not a healthy application, let's say, from the point of view of high performance computing, of course. Auto-optimize is an iterative process. You code your code, you write your code, you do a little bit of performance and monitoring analysis, then you try to tune your program, and then once you are satisfied, this is actually an iterative loop, once you are satisfied, you go into production and run forever. Remember that the iterative optimization, that is this loop, has three different aspects. The first one is actually to check for correct answer. So before doing any kind of optimization, well, once you have coded your code, you have coded your program or your problem, okay, you have to check that it works. Okay, in the sense that it gives you reasonable and physical and feasible results. Okay, then when you are sure that the code is working properly, the regression testing and so on, mentioned yesterday by Luca, you can start optimizing, okay? You can then profile to find the hotspots. That means the section that are actually the most time-consuming part. And then you start optimizing them, and then you go again. Remember that this point should always be done. And this is actually not a trivial, it seems that it's actually a trivial tips, but not all people does that. And remember that when you are trying to optimize a code, it could be that you optimize for a specific data set or for a specific input of your code, and then you optimize for that, and then you run all the tests, and you see that some tests does not even does no more pass, just because you broke something for that specific test. So be careful about that. I mean, with Geotop, that is actually the code that that guy knows very well, we run into several problems about that because we were trying to optimize a few things, and then on some tests everything was okay, and then we ran for the general tests, and we see that some tests were not actually passing anymore because we introduced some kind of specific optimization that actually broke the scientific validity of the code. And this happens very often. So be sure that you have a very large number of tests to validate any single step of optimization you are performing. Okay? And about the optimization techniques, there are mainly 3 optimization techniques. The first is actually to improve memory performance. That is actually for sure the most important one, because once you are accessing the right way the memory, half of the work is done. Then you can improve CPU performance, and there are a lot of tricks you have to improve by pipelining, by means of using vectorization, and so on and so forth. And here, the trick is actually to make your code easily understandable by the compiler in order to optimize that. Now then there is also another one that is actually to use already highly optimized library as a subroutine, because in this way, I mean, you can really make a great difference, okay? Because we don't want to reinvent the wheel, okay? This is actually another important point. But the point is actually what are actually these performance libraries? Well, are routines of mathematical function, okay? Like matrix linear algebra routines, that are actually probably one of the most important points. Fast Fourier transform routines that are written in a way that you can really exploit the kind of technology and the kind of capabilities you have on your CPU. Okay? And so generally each CPU vendor provide its own version of the library explicitly written in the right way for that kind of architecture. Okay? And so why do we have to use them? Well, because I mean, there are people that are much better than us to write a mathematical kernel library on a specific CPU platform like an Intel one. So Intel engineers are generally, they spend their life doing their professional life writing this kind of algorithm. So you can't think to be better than them. Okay, so the idea is to say, okay, they wrote for sure, they know perfectly the architecture, so they wrote for sure a very nice library. So let's use it and don't waste our time in coding something that has been already done. Don't reinvent the wheel. Okay, of course, you as a scientist, you as a computational scientist, it's always your responsibility to check that the library that you are using that is quite efficient is also correct from the scientific point of view. And this is actually another important point. Okay, so you're smart. You always have to check that what you are using is actually the appropriate tool and is not actually breaking, and the tools that you are using are not breaking the validity of your scientific application. Okay. Well, this is going on. And then there is another reason apart from optimization, is actually that makes life easier, because you can build your application in a simple, let's say, Lego approach in which you have your code, and for all the linear algebra routine you don't have to reinvent the wheel, but use something available, and then you can replace things in an easy way. You have your code, you make your code portable. That is another important point, portable and efficient on different architecture, because if you code your code, if in your code you use linear algebra routines, okay, they have a standard interface, as we will see in a moment, and then when you move from Intel to IBM or from IBM to AMD, you just replace the library, and you don't have to touch your code. So you keep your code portable and efficient at the same time. So that's actually another important point to use. So it happened to me to see people that wrote down their linear algebra routines, saying that they were so satisfied about that because they were able to carve out a very specific case of the linear algebra problem they have. That's correct, okay, but then they port it on a different architecture, and performance were really terrible because they carved out the very specific linear algebra problem for that specific architecture, and once they port on a different architecture, everything is gone. You can rely on linear algebra routines done by others that can be portable, and it's much better sometimes to go this way. What is available? Well, tons of libraries, okay. Here we have, I should probably update this slide because, I mean, I inserted just linear algebra stuff, I inserted fast Fourier transform stuff, I inserted partial and ordinary and partial differential equation. PETSI here is actually one of them, but there are many others here. And also now there are tons of library for artificial intelligence, of course, TensorFlow and stuff, and even well, TensorFlow is a high-level library, but behind TensorFlow there are tons of other small library specifically written for machine learning problems. Good starting point, even if a little bit biased towards this kind of environment, scientific environment, not data science environment, let's say, is actually www.netlib.org. But actually, to do your computational science in the right way, once you have a fast Fourier transform FFTW installed, and you have it in the cluster, and then when you have a very nice, a few linear algebra tools installed, you are okay. Linear algebra, for instance, let's discuss about BLAS. I will come to it. I mean, subroutine have a standardized layout. BLAS is documented in the source code. Man page existed. The vendor supplied a lot of documentation, and of course, any kind of routine that you need in from BLAS library is always actually called in the same way. And here I don't know if you are able to read, but it's actually the way you call dgem, that is actually the general matrix multiplication routine that multiply matrices. And what do we have about BLAS and LAPACK? Well, we have the Intel Mathematical Kernel Library. That was the one that I was trying to use on your cluster here. That has not just BLAS and LAPACK. BLAS is the basic linear algebra system, and the LAPACK is linear algebra package that contains mainly all linear algebra routines that you can think to need. Intel Mathematical Kernel Library also have FFT and also have signal processing routines and a lot of other stuff. It also it runs very efficiently on all the architecture. Atlas is also another routine, another library, interesting for LAPACK and BLAS. Atlas stands for automatically tuned linear algebra software. So when you compile the routine, the library actually takes well, ages. A few years ago it takes ages. Now I don't know how much it takes because we don't really use anymore this. I saw that on the cluster is installed, so probably some user ask you to install Atlas, no? And that could be useful for some users. But in the idea behind that is actually that it tries to compile. It compiles the library, then it compiles some kernel, and then it tests the kernel on the architecture that you are, and then it tunes the kernel for instance for matrix multiplication. It tunes the kernel in order to take into account the size of the caches, the architecture, and so on and so forth, and define and find out which is the best algorithm that works on that. So it actually compiled 10 different matrix multiplication algorithms, and then test which is the best one for this specific architecture. So that's why we have this automatically tuned here. There is also OpenBLAS that I asked Michele to install. OpenBLAS is actually a quite good project. It's actually a very limited library that in any case implement in a very efficient way a few routine of BLAS, and in this routine, in this library, there is really some incredible tricks in order to optimize, especially BLAS operation. It actually came from the GoToBLAS, and GoToBLAS is actually a BLAS library invented by a guy that was called that is called Goto. This is a Japanese guy that spent his professional life in writing just matrix multiplication algorithm in the best way for all the CPU that he has available. So he's actually did an incredible work, and now this work is actually on OpenBLAS. OpenBLAS is actually an open source library, the same like Atlas. Intel Mathematical Kernel Library is not open source, so you have to buy the Intel compiler, but it's not really so much expensive. How many of you knows this kind of library? Okay, which one? Yeah, because you need to compile Quantum Espresso, and so Quantum Espresso rely on them. So, by the way, Quantum Espresso, if I remember correctly, came also with a LAPAC by itself, just to be sure that you don't have any trouble. But in order to get performance, you have to use this one on Quantum Espresso. And you, what are you using?
I use OpenBLAS, but
okay.
without. I have an interface. I have a library which.
Of course, yeah, uses OpenBLAS or whatever.
Which uses OpenBLAS.
OpenBLAS is actually quite efficient. Of course, is not so as efficient as Intel Mathematical Kernel Library. So maybe, yeah, it's a little bit better. It depends on which kind of operation you do. But on Intel cluster, Intel Mathematical Kernel Library is not actually. There is nothing better than that. And I didn't mention too much about AMD Mathematical Kernel Library, just because the ACML, because AMD, I mean, is now coming back to into the high performance computing world by means of this EPIC processor that was released recently, 1 year ago. But before 1 year, before the release of EPIC, AMD was completely disappeared from the high performance computing world, just because the processor was too slow with respect to Intel. And actually, at a certain point, we still have a cluster based on Opteron, and we also install Intel Mathematical Kernel Library on this cluster, and we saw that for some problem, the Intel Mathematical Kernel Library was actually even faster than the AMD Mathematical Internal, the AMD Math Core Library on the Opteron and on the AMD core itself, on the CPU itself. So it's really, they did a really magic tricks into that. And so, and I got the fee, and I also did a benchmark a couple of years ago, because we were developing a code using Intel Mathematical Kernel Library. Okay, actually the code was written in Python, so we use NumPy, and NumPy, you know that if you have NumPy, and you install NumPy without knowing anything, NumPy comes with a very basic and quite poor performance, BLAS library. Okay. So it comes with the netlib.org library that you can download, and it compiles it. So if you are actually doing a lot of Python computation and you do a lot of NumPy, I strongly suggest you to check which is the BLAS library that you are using with Python. We were using actually Intel Mathematical Kernel Library behind our Python NumPy library. And we provide the final code. We provide the final code to our client, and they tried to run the code, and they were complaining that the performance were not good enough, and we were a little bit surprised. So that we log into their cluster, and we checked that NumPy was the default one, so with really horrible performance. They didn't have MKL, and so I just recompiled NumPy by means of OpenBLAS, and actually we were able to gain a factor factor of 6 with respect to the original performance, but we still have a factor of 2 with respect to MKL on that specific code. Just to tell you the kind of performance that you can see. So maybe if you are intensively using this code, maybe you can just to check if MKL is a little bit better than OpenBLAS. And again, it should be just replace the way, I should have it here. Yeah, you have just to replace the way you are linking your code, nothing but that. And this is actually the power of using libraries, no? Because you just have to say, where is my linker and where is my library, okay? You have to be careful. If you use LAPACK and BLAS, you have to specify the correct order, but now if you go for MKL, it's actually MKL uses a collection. It's actually quite complicated to find out the right way to compile with MKL, but for this you can go on this size, on this, on this site that I should have here somewhere. Let me see where is, I don't see my screen anymore. Where is, let me see if I'm able to find out. Yeah, so here you see so you can specify which version of Intel MKL you have, the operating system that you have, the compiler that you want to compile against. Well, let me see, for instance, Linux. So you can also compile MKL against GNU, so no problem about that. Then you select Intel. Okay, then dynamic or statical, dynamic, the interface, 32-bit, the threading, OpenMP, sequential, whatever. TDB is threaded library provided by Intel. And then if you want a cluster library, the MPI library if you need it, and go for that. And here you see you have the line that you need to insert into your make files or you need to use. Okay, and of course it also refers to this MKL root variable that is actually the one that I was trying to see which way is set in your cluster, because this should be set automatically and there should be some trouble there to fix and to see maybe now at the at the coffee time, because we are now now it's coffee time, so we can just stop here. I still have a few slides on BLAS that maybe, let me see. Yeah, maybe we can actually, well, we do later. Okay. Okay, so let's go for a coffee, and then at 3 we can gather again and go on with the exercises. Come mai non vedo la MKL root? Questo che non riesco a capire. Perché qui le librerie ci sono, quindi, perché c'è, insomma, no, in realtà non sono sicurissimo che ci siano, perché se entro qua dentro poi vedo sta roba. No, ci sono tutte. Quindi questo c'è. Quindi le librerie ci sono, però la MKL root, perché aspetta, fammi vedere come ha definito qui adesso che ho guardato qua. lui me la definisce come mkl root e libintel 64, quindi deve stare sopra. Quindi se io definisco libintel 64 cd intel 64, ok, perfetto, e quindi la
Vediamo dove
mkl
siamo
root
qua, deve
esatto,
essere.
questa sopra,
Ok, quindi bisogna fare una variabile.
questa, quindi devo fare un export
Esatto.
mkl, no, root tutto unito uguale a sta roba
quella
qua.
roba lì.
Sbatterlo nel modulo.
Esatto, te lo metto
Esatto,
nel modulo.
bisogna metterlo nel modulo,
Prova a
questa roba
vedere
qua.
se funziona, la mettiamo.
Esatto, fammi vedere adesso, torniamo su, dov'è che ero, cd, hpctn.
Questo sia nel 2018.
Sì, è quello del
Ok.
2018, non so perché avevo quello del 2018,
Dov'è?
module list, fammi vedere. Intanto vediamo se il
Sì, sì,
2018
infatti
funziona.
vedi
Sì,
se
adesso
va.
ho tirato sul
Sì, sì,
2018,
vabbè, ma
buono.
non importa, tanto sarà lo
Allora
stesso.
esatto, vediamo, è multicore, CPU, cd, node perf, mecc, node perf, aspetta adesso com'era la linea di compilazione. Così.
Poi ti ho messo su gli altri due, il Numa CTL.
Ah, sì? Ah,
e
perfetto, grande.
L'hardware
Comunque,
lock.
la dotazione software del
Sui
nostro
moduli.
cluster fa capire il livello
Di uso.
di advance del
Esatto,
nostro
non
utente.
c'abbia niente.
In che senso?
Sì, nel
Aspetta.
senso che sono cose che
Il fatto stesso, esatto, che non funzionino è significativo.
Aspetta che vediamo un po'. Allora, devo compilarlo però il coso. Porca peppa, adesso. Module list. Ok, c'ho l'MPI. Allora fammi vedere il readme, come facevo a compilarlo per il readme. Ecco qua, questo, devo provare questo.
Vai.
Cannot find L, MKL sequential, MM core. Meno I, MKL root, lib, perché gli dico ILPS64?
Invece di Intel 64. Era Intel 64 mi pare, no?
Sì. No, però le ha trovate,
li trova, però
c'è solo che gli manca adesso, ma questo dovrebbe essere solo questo. Meno L, MKL. No, aspetta, vabbè, a parte che adesso però mi posso fare la rigolina così, perché a questo punto gli dico che era il 2018,
Poi te lo
Linux,
metto anche su
Gufortra,
2019.
esatto, Dynamic, 32, esatto.
Sì, sì.
No, aspetta, reset, rifacciamolo. Allora, Linux. No, Fortran. GNU Fortran, perché... No, GNU C. Intel. Eccolo qua. Select linking, dynamic. 32. OpenMP. Intel.
Stefano, che devi fare tu ancora?
No, voglio solo vedere se mi funzionano le MKL qua sul cluster. Dopo io niente. Ciao Gino, come va? Tutto bene? Andiamo adesso, guardo solo se mi funziona.
Ti aspetto su
Sì, dai, arrivo subito.
Subito curioso vuoi chiudere qualche vago?
Meno as needed. Vediamo un po'. No, ma aspetta, ma... No, c'è qualche casino sul coso, sai, sul... Cannot open output file, node pair, infatti c'è qualcosa di sbagliato qua. Sta copiando male la linea. Perché? m'ha fatto un casino al terminale. Facciamo così, apriamo un altro shell con pulito, esatto.
Sì. Adesso HPC 2019, l'anno scorso più che...
Perfetto, CD anche PCTN, multicore, node perf, ok. Questa era la
c'era
linea,
lì.
sì, esatto. E adesso facciamo, però adesso devo fare il load.
Giusto.
Load,
Intel.
OpenMPI. No, prima il MPI
ok,
e il GCC ce l'ho, quindi MPI CC adesso ce l'ho.
Ok.
Perfetto, quindi adesso faccio MPI CC-F OpenMP di node perf C. Ok, e tutta sta robaccia. Puff.
Il modulo...
No, adesso no.
La variabile.
no.
Non è nel modulo.
No, non è nel modulo.
Il
quindi,
modulo, esatto, non c'è
e
nel
quindi
modulo.
è apps, però lo troviamo perché
Apps, Intel
apps,
e apps, vedo,
no,
ok,
perché non,
Intel, quello 2018 con la I maiuscola.
Intel 2018.
No, Intel
Parallel Studio.
si
Intel
fai
Parallel Studio 18.
ok, vai, tab,
Update,
e
dopo
qui
siamo
c'era
andati in
direttamente libreria MKL
e
basta.
basta. Ok, perfetto, questa. Allora questo adesso tiro su, lasciamo questo spazio per rompere balle.
Boh.
Ok, sì, perché adesso l'unica che non trovo è l'IOMP5, perché quella è la libreria OpenMPI del compilatore che va tolta, però se tolgo questa dovrebbe compilare. Certo, infatti lui si incazza perché mi dice ma tu mi hai chiesto di compilare col KMPC perché gli ho fatto fare sta roba, perché gli ho messo le MKL in thread. Aspetta, ma basta che cambi la linea adesso, aspetta. Invece che dire, invece che dire che no, fare questo, fai così.
No, infatti volevo dirglielo prima però.
Ecco, adesso questa è la linea. No, era solo. Questa è la linea. Adesso dovremmo esserci.
Vai.
E adesso mi serve solo un caffè. Grazie ragazzi. Mi scuso per non avervelo detto prima, però insomma. Aspetta, questo lo tolgo.
poi come sparse order a quel punto lì cosa si usa? Cioè,
Ecco, questa è una cosa su cui io non sono un esperto, su sparse metrics.
Signori, io vi ringrazio. Paolo.
Grazie, piacere, grazie a voi dell'ospitalità, è un piacere essere qui,
Sono poco
veramente.
presente.
Ci stiamo divertendo.
Lo
Noi
so.
sì, almeno loro non so, a tratti,
Io
penso.
comunque mi tengo d'occhio, il remoto.
Fate
Sai
bene.
che c'è il coso, come si chiama?
Fate bene.
Funziona benissimo.
Sì.
Segue molto bene. Seguito con la propria stamattina.
Ah, ecco, ottimo.
Up to date.
Up to date, bene, adesso facciamo giusto un po' di esercizietti.
Mentre ancora attacchi
Sì,
le ultime cose.
sì, dimmi.
Volevo solo ricordare chi
Vai,
ha
vai.
bisogno del diploma, in particolare studenti o che, di ricordarsi di firmare, insomma, diciamo che ci sia almeno una presenza superiore al 50%, ecco, insomma. Quindi io questo continuo a lasciare lì, poi domattina vengo e distribuisco i diplomi. Se c'è qualcuno che non era previsto e che si è aggregato, me lo fa sapere che possiamo dare anche un diploma. Vabbè, solo questo.
So, ok. Okay, so well, just few words about an effect which is related to the cache that you may encounter. Well, this is an example that uses matrix, dense matrix transpose. Basically, if C is the cache size and LC is the size of a cache line, you expect basically three different regimes. So more or less, either both of the matrices can fit in the cache, so basically you don't have to bother about anything, or basically one of the one of the metrics fit in the cache, and or otherwise you have very large matrices, okay, and each access to the matrix to be transposed determines basically a compulsory cache miss and a write allocate. Okay, so these are three different regimes, and basically here is what you get. This is the bandwidth in megabytes per second. This is the size of the matrix, and this is the set size in units of L1 line capacity in terms of double. Okay, and so you clearly see there are three different regimes. But the point here is that here there are very few points. But if you perform this calculation for basically all the values here, you find that in some places it is really noise, okay, the performance that you have, and in some places you have for some values you have an incredible fall down of the performance. So you have a very high bandwidth for whatever n, and then for n plus 1 you drop down by a factor of 10, 100, something like that. Okay, so you say why? I mean, it's still in the cache, no? For instance, so what happens? So you already know, because this effect about the the strided access in reading or in writing in the cache. So writing is worse, so it's better in reading than in writing. And but there are also other effects. So these ones. And what is this? So basically, this is an effect related to how the cache actually works. Okay. So let's say that you have a cache of size C bytes in total, and let's say 8-way associative. So associative, I just recall this, means that you have, if this is your cache, you have a number of lines, okay, and they are grouped actually. So you have a choice in this, let's say 8 choices, so that a given address is mapped on a group actually, not just on a single line, in the sense that if it falls on a line that is already occupied, then it has another choice and another choice and another choice. So W choices, okay? Normally it is 8-way. So typically a line is 64 byte, the associativity is 4 to 8, and the total capacity is 32 kilobyte. Okay, so how do you map a memory address to a cache? Okay? So what you have is that you use B bits, which is the exponent that you need to have the cache line. So the most significant B bits to determine and to choose the line, and S bits, this S here, to determine which set of lines, okay, you fall in. And so at this point, you know basically everything. So given an address, you can determine to which set it is mapped on and to which line it is mapped on. Then, if that line is occupied, you can go through the other lines. And then you also save the rest of the address. It is called the line tag, because at that point, if you have a location here, you have a degeneracy, okay? You wouldn't know exactly where in memory should be mapped back, okay? So you need also this part of the address to restore the actual address. So this is how the cache actually works. So what happens? So let's say that you are accessing your matrix. Now you are transposing. So you access the matrix in this side like this, for instance, and on this side like this. Let's say that you are writing these two locations here. So you access the element J and J plus 1, and the stride is obviously these ones, okay? So N, where N is the dimension of the matrix, and W bytes is the bytes that it takes to go from here to here, okay? Because, okay, you see the matrix in 2 dimensions, but obviously it's just 1D, it's a chunk of linear dimension in the memory, in the RAM, okay? So the offset from here up to here is n elements of the memory, doubles, float, whatever it is. So W bytes, okay? So if n is a power of 2, there is an exponent n small, okay? So n is 2 to the n small. And W is also a power of 2 because, of course, you know that the types in the computers are always longer. The length of a power is a power of 2, okay? The length of a type is a power of 2. So let's say D, okay? So the offset actually is 2 to the n plus D. You follow me? Quite elementary math. So if n plus D is larger than B plus S, where B and S are these ones, okay? The address of J and J plus 1 is mapped in the same set than IJ, okay? And then, so you have, let's say that the blue point is here, blah, 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 blah. This is the yellow point, and they have the same set. It may happen by construction. It will happen actually, for sure. Okay. So at this point, what happened? That the blue one goes here, fine. The yellow one goes here, but okay. Then it changed lines. Then another one, because n is large. Okay, so you have a lot of time this effect goes on the third line, the fourth, and the seventh, and then what happens? That you have to go on the again on the first line and so on. So you have to flush, okay, and you continue to flush. And when this happens, you see clearly the effect on the bandwidth that just drops down. This is called the cache resonance. So you have hit exactly the n, the combination of n and of the type that leads to the cache resonance. What you can do is to pad, actually. You can try to alleviate this kind of effect. Just padding, it means that you just add a fake boundary layer in memory here, which is large enough so to break this effect as much as possible. Okay? And I mean, there are a lot of research. This is a paper about this fact. So what are the best strategies for this and so on. So it's kind of a serious affair. So the violet line is the naive version, simple version. And the green line is just with swapping. So the strided access is in writing and not in, is in reading and not in writing, okay. And the blue one is the naive one with the padding, okay, and the yellow one is the naive is the swapped one plus the padding, okay, and you see that, I mean, this is log scale, and you still have an average bandwidth which is, I mean, even larger, okay, and you alleviate the effect of the resonance. I mean, here is not that much evident because I use just few points, okay. But we noticed this because some of the students that were they were asked to calculate the bandwidth why the dimension of the matrix was varying, and some of the students, do you remember, Stefan? They were calculating it for every n, and all natural numbers between 1 until 2000s, or 10,000s, and they came up with this, absolutely. Understandable, and then for some values, brand, again, oh, what happens? So, is this? Right. So, that's kind of curiosity. I mean, just to give you the level of details that you have to care about when you go for this kind of stuff. And, you can, I have uploaded a new exercise, 05, in the repository, and you can go. So let me log in your cluster. I'm exiting here. So SSH. Okay. Okay, so this is just another curiosity. So this is a small code that allows you to inspect where your threads are running on, okay? So what it does is very simple, sorry. So this is the main, and you create a parallel region, an OpenMP parallel region, and then you get your thread ID, and then each thread calls this function get CPU ID, okay? And this gives you the the ID of the core on which you're running, and then you just print out the information. So you have the list for all the threads where they are running, so you can check, you can play a bit with the environmental variables, okay? So you can try to put all the threads on a single core, or to spread, or just on a socket. So you can play a bit, and you can check what happens and understand how it works. So this function is quite simple. Well, it's this one. There are some if-def just for you to play a bit. Now we are using this one, this syscall, okay? And but actually, you can read the proc self-stat, because actually all these techniques use the information that the kernel exposes. If you go here, y proc self-stat. Ah, no, because we are in the node here. Okay, no, on the node you can't. So, no, we are on the master. So why? Self, okay. Start. You have this wonderful list of strange numbers here, okay? Actually, this are a lot of information starting from the PID, and then this is the PID, and then this is the command line, and inside here there is also the information about the memory that you're using and the CPU that you are using, and so on, okay? Yeah, it seems strange, you know? There is there. So let me just go q sub minus I minus L nodes equal 1 n equal 72 minus q. How is that? Is the name of the q? HSPC. Scientific High Performance Computing. 2019. Yeah. Small caps. Capital. Okay. Fine. So export OMP display equal true. Fine. And then you have all the informations about the environmental variables, because there is this variable OMP display environment. Okay, if it is set true, when you create the first part of the region, OpenMP write this information, so you know what you're doing. Okay, so dynamics false, nested false, num threads is 72, Chevrolet is dynamic, and blah 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 blah. Okay, just as some information, and you see all the threads. Okay, so thread 16 runs on core 41 on this host, so you can understand exactly what's going on. Okay, and also you have, I mean, there is the code. You can learn the technique. You can explore what it's doing and reuse that code in your codes. Okay, that's the way things are used to be. Fine. So, and then I leave to you just to change the places and proc bind, for instance, no? So, export OMP places equal socket, export OMP proc bind master. Well, see that now the numbers here are not spawning from 0 up to the maximum, but if you just count, you will see that there are several threads that run on the same core, right? And that is because we asked it for. Okay, core 11, core 11, 14, 14, okay? Because I asked that these two facts here, so places is sockets, and the binding policy is on the same place than master. So since the place is the socket, then it will use all the cores of the master socket. Okay, and in fact, that is what happens, right? So you can play a bit and understand how it works, no? But I mean, funny, okay, okay, for nerd people it's funny, yeah? Sorry. That is. Well. Okay, I wanted just to show you this. And well, fine. Another exercise, well, no, okay, fine. Stefano, do you have anything?
Another exercise, because I have now just a few exercises to propose. More than that.
Well, I was wondering whether to show something about, just one more thing that can be useful in general. Okay. Already know about this. Sorry, I'm driving. Okay, prefetching. So, what prefetching is? You already know everything about cache, okay, so how much important is that the datum is in the cache when you want to use it. But if it is not on the cache, what the hell can you do, okay? Well, you can prefetch. So basically you can ask your CPU to preload, because you know that in 10 minutes, so in 10 minutes I would like to have the coffee, so I'm just I want to be sure that the coffee is ready, so I will call my friend, just put the mocha on the blah blah blah, no? So just exactly the same. So there are techniques for this, okay? Basically, you can either have an explicit prefetching or an induced prefetching. Explicit is that you use an instruction, which is exactly that, prefetch, okay? But that is really difficult to be used well, in the sense that it's really delicate, because you have to put it in a code, and then when the assembler is generated, actually it may be moved. To understand the real good point is not that easy. Or you can induce, okay, which is much easier, and I'll show you how. So this is an example. So this is a classical binary search. Okay, you know what it is, a binary search. So you have an ordered array. Okay, and you want to search for a value. You start to you pick up the mid value and you compare with your value. If your value is larger than this, then this becomes your new array, and you pick up the mid value, and again, let's say now is smaller, then this is your new array, you pick up the mid value, and you continue. So basically in log 2n, where n is the dimension of the array, okay, you find your value. Okay. So what happens here is exactly this. So you compare. So until low and high are the two ends of the array. So until you have more than one element in the array, you pick up the mid value and you compare. If the mid value, this is the mid position, this is the mid value is smaller than the key, so the key is larger, then you go for the other side, and in the opposite case you go for the left side. Okay. So in the first case you put that the low is on the right of mid. On the other case the high is on the left of mid. Okay. And the low was already at the left of mid. So okay, it works fine. However, what happens if here you put these two prefetch? This is a built-in function of the GCC. Okay. What I'm saying here is, so since I know that either this one or either this one will be used. This is the mid of this part, and the other one is the mid of the other part. Either one of the two will be used in the next iteration, for sure. Okay, because either I'll go on the right or on the left. In any case, my next comparison will be this one. Okay, and so better that this datum is already there, right? So, since I'm a clever guy, I tell the CPU, okay, give me both, because I don't know which one I will use. So just put both on the cache. So what happens? Exactly the same code without the prefetching and with the prefetching. Just because the datum are already in the cache. Okay? Just quite a good result, I would say. No? So yeah, it is clear why. You cannot see, I'm sorry, this is red over blue. But in any case, you have the, here you have the, what changes here is that L1 hit is less than 1%, and here you have 30% basically. And also the LFB, okay? Instead here you have a local RAM hit is 70%. So 70% of the time you have to get on the RAM. Well, okay, this is the explicit prefetching, and that was quite a simple case, and I was really lucky because not that easy to have such a huge performance with just one line of code. I mean, it is because it really really simple, that code. Okay, so it was easy. What happens here, however? So let's say that you have an array and you want to perform some operation on the elements of the array. No? Let's say that these are double. Okay, so normally you will have a cycle, and then you elaborate the element I. Okay, then you have the element I. Let's say this is double. Okay, then you fill the cache, and you are lucky because you have all the 8 doubles that you need. Oh, fine. But you can do something different. You can perform an unrolling, okay? And then what you do is that outside, A is the first element, okay? So you load the first element on A, and then on B, C, and D, you load the other elements. So in the first occasion, you have, of course, a compulsory miss, but that's unavoidable, okay? And then you elaborate. However, what happens? That in E, you call for the next one. So this is the first of the next bunch, okay? Meanwhile, that you are loading and elaborating, it travels from the memory to the cache, and here you assign it to A, okay? So it's already there. Then, again, you say, okay, then you increase I by 4, so this is, again, the new one of the next bunch of 4, but now B, C, and D are already there. You can unroll by 8, for instance. It's even more effective. And then you elaborate, and so on. This is induced prefetching. Okay? Is that clear? The concept?
Induced, but by a proper
Yeah.
structure of the code. Because I jump over
Exactly.
to let the new data.
Exactly. This is possible because the CPUs are out of order and have different ports. Okay, so the CPUs understand perfectly that this is just a load. Okay, and then just fetch this to a port, and then this for other ports. Okay, it dispatch this whatever it is. Okay, to other ports, and this is a code snippet that I will upload this example so that you can play a bit and see what is the difference between among the different versions. Okay, I will upload 4 different versions so you can understand what's happening. And okay, that is another well, useful thing that you can try to take into account. Okay, in your code. It's not really that easy to do that, but once you set up your mind about this, exactly as you were saying, then you try to write your code, to design your code in a way that is possible to expose this kind of stuff. You know? Well, I'll leave you for exercise proposals.
Okay, so in this last hour, what we can do is actually to play a little bit with the cluster and to play a little bit with some of the tools that I show you. Now let me just do this way again, so we got the right. Okay. Okay, so I'm here. I have this guy, the multi-CPU, multi-core directory in the repository we created. So if we go there, I have 3 different things to do. One is node_perf that we tried to compile before, and actually I succeeded in doing that. And now I can see that my LDD on output is actually this way. Of course, there are a few libraries still missing because I don't have inserted yet the LD library path with these MKL routines. The compilation actually was. Let me see if I remember. Yeah, this is the way we compiled the code. So, you know, MPICC node_perf, then I linked the Intel mathematical kernel library that we discussed before with in this way, and in this way is actually not in this way, actually in another way. Let me see. History. In this way, it was actually the right way to go. Okay, so here I actually asking to compile the code using MKL in the threaded version. So we have multiple thread that linked against this library, and I ask the library to use the GNU threads library. Okay, and that's why I have these 2 stuff here. Okay, And of course I can't remind by heart this kind of command line, and to do that I went to this place over there. That is, no, it's not this one. Where is I lost it, but in any case it was on my slides, this on the slides that I had provided you. That where are now? Here it is. Okay, no? So I ask the library, the version, again Linux, the compiler, the architecture, the dynamic way, interface layer 32-bit, OpenMP threading, and when I say threading library layer, OpenMP threading, and then I say OpenMP library, I selected GNU library. Okay? In this way, the command line, the resulting command line was this one. And you see that I have here GOMP and MKL GNU threads. If I had to choose the Intel one, okay, you see that I should have this MKL Intel threads and then OMP5, that is actually the OpenMP library coming with Intel. I choose this just because we are using MPI, we are using GNU, and it was a little bit simpler this way to compile the code and be sure that it's working the right way. So at this point, okay, I have a file that, I mean, I have an executable that that have a lot of other library, a lot of dynamic library, that it needs to load a lot of dynamic library, and in this moment I'm actually missing this library over there that are actually MKL library, just because MKL is not yet, the MKL path is not yet inserted in the LD library path that comes with the modules. Okay, so I have to add it explicitly, export LD underscore library library path equal LD library path MKL if still defined lib Intel 64, hopefully. And then let's see, and now I see that all the library dynamic library are resolved. Okay, yeah.
MKL is proprietary but is free. How does it work?
It's proprietary but it's free, but you have to have the compile. I mean, I don't know. Can you download now? It's free?
Okay.
I'm not pretty sure. Yeah, you don't have to buy MKL, but you have. I mean, if you buy the compiler, MKL comes for free. That was I was aware of, but maybe things have changed.
They change the policy every time they put up
Yeah.
Okay.
Yeah. So in any case, now on the class,
Just go to the Intel software developer site, it search for MKL, and you find immediately.
yeah.
No, it let me download the version, but I don't know.
It let you.
Yes.
But is are you entitled to use it for evaluation or just forever?
That was my question.
In case you evaluate forever.
No, because I mean it's a little bit complicated. By the way, in any case, for students, if you qualify as students, there should be a perennial license for Intel Parallel Studio.
Okay.
So check this and whatever. Okay. In any case, you got it. You can get it, and on the cluster is actually there because somebody paid a license for the compiler. Correct? Yeah. Okay.
Okay,
So
perfect.
you can use it. Okay. So in this way, now we have everything ready. Okay. And so we have this node perf that is actually a piece of hardware that is that was created by Intel to show how good are their compiler, their library, and their hardware. So it's something like that. So we can actually try to run it and see what's happening. Okay. So it says, for instance, that is a multi-threaded MPI application. Tomorrow we will discuss about MPI. It looks also if there are CUDA aware stuff. So we don't have this kind of stuff here, and so we go for that. We go without CUDA, that is actually the software environment to compile and to compile code, to write code and compile against GPUs. I have also an example in using GPUs, then we can use later if time, well, or maybe tomorrow if time is left, and this actually stuff. So you see, this is actually the output of the code. Okay, now I don't remember exactly how many input. So it allocate this. And this is actually performance that you can get. And this is actually echo LD echo. I would like to check my OMP num threads. That was set to 1. So if I now do export OMP num threads equal 72, okay, let me see, there is, am I alone or not? My terminal is not working correctly when I increase the font. Let me see now here. No way at all. Let me open another shell. Okay, so it looks like that there is nothing on the machine, so 100% idle. Well, I don't want to increase the font because, well, let me see. No, it's gone, I don't know. But in any case, there is nobody there. So I was here, so I exported OMP num threads, and now I can try to run this again. And let's see what we can see now. But still, again, it runs. So this is the number I get when I run on a single core. Okay, that is 72 gigaflops, and this is when I run on the overall machine. And this is actually the number. That is something like 10 times faster. Are you satisfied with that? Not at all, of course, because it doesn't seem to scale well. And then why this? Let me see if we do this way. This is actually alpha. Okay, and we have now 1.4, so it's actually something like 20 times there. no? It was 72, and this is actually something like, yeah, it's something like 1043. So it's 20 times faster when I run on 36. Okay, but when I run on 72, it's actually quite fluctuating, because now it's a bit better, but but it's actually fluctuating. But in any case, it doesn't scale linearly. Why this? Any guess? Well, by the way, what is doing this? This is simply doing a matrix-matrix multiplication, okay, on a size of the matrix that is actually 15,000 elements. So it means that we have a 15 times 15,000 times 50,000 square matrix, and we are actually multiplying it. Well, we are multiplying matrices of this size, and actually the size is actually quite relatively small for the overall architecture that we have. In order to increase the performance, what we should do is actually to increase also the size of the matrix. Okay, and then if we have this small matrix that is actually accessed by 72 threads at the same time, we can have a lot of resource contention, and that's why it doesn't scale too much. Okay, the behavior is not actually what we are expecting. We should increase the size of the matrix. Okay, so you can play a little bit with this tool and see. We can also run MPI run, because MPI is here. No, I have to load module load open MPI. Okay, MPI run minus NP2 a.out. You see, now it's running on 2 nodes, okay, independently. Tomorrow we will see this, okay. But in any case, here what we are doing is actually running an MPI program, so it means that it spawns more than one process on different cores. So we can try also 72 and see. Of course, because I have asked how many? I have asked just 4. No? So I have to resubmit. Okay, now I have to load this. Of course, because here I have to go on HPCTN. Yeah. I have to set also the environment, because my LDD a.out is now missing this, because I set the export variables. So export LD. Sorry about that. Library path equal $LD library path, and now this time I can't rely on the MKL root variable. I have to go by heart apps Intel Parallel Studio 18 MKL, correct? Yeah. No, not not NKL, but also NKL lib intel 64. Okay, everything is there, and then I can run on a whole there are a lot of error here that I don't want to comment today. I will comment tomorrow on this because this is actually related to the InfiniBand network. Okay, so it runs on all the node, on all the cores of the machine. By the way, we can see something like that. If I do this, you see, this tells you that it's not working correctly. This, no, because as I tell you, no, you don't see probably. Let me just try it for now. So this is actually what I did is actually I prefix my program with user bin time, okay? And user bin time is reporting the user time, the wall the lapsed time, that is the wall time, and also the user time. Okay, and then I do this way. Okay, I execute the code and I got these numbers. Okay, I got that this is actually the elapsed time, that is actually 5 seconds and 22 something. So this means that it takes exactly 5 seconds from when I issue the command up to the conclusion of the command. Okay, but then I look at the user time that is much larger than 5 seconds. Of course, because the user time is actually the sum of all the time allocated to me, to my process, by all the cores involved in the computation. Okay, and so I have 51 seconds. And you see that the CPU, the ratio between CPU that I told you that should be actually always 1 if you run a serial project, always 100% if you run a serial project, now is actually something like 22,000. So it means that it used at best 22 cores of the of the 72s that I have at disposal. Okay, and you can understand that is actually not a very good behavior, because if it scales perfectly, this OpenMP application scales perfectly, you should see here something like in the order of 7,000. Okay, because all the CPU are then used 100% to my application. There are actually I'm using very little, and I can see that is something that there is something wrong here. System time. So you have 62 seconds of system time. It means actually that the CPU, the operating system is actually always struggling in defining where to put my threads and so on and so forth. And so actually this code is actually completely doesn't scale at all, because there is too much overhead associated in the management of the threads for such a small problem. Okay, we can see, and we should see actually, let me see if this is true. Okay, if I do export OMP num threads equal 1, okay, and now I'll do that. It will take a little bit more, of course. Okay, but I see that I have 97% of CPU. That sounds reasonable now. Well, not so reasonable actually, because you would like to see 99%. And in fact, I mean, you know, I have that the total time, the elapsed time is 8.62. And out of this 8.62, you have 6.70 dedicated to my calculation, but still 1.63 dedicated to the operating system, to the some operating system calls or whatever. Okay, so again, sounds that is not really optimal. This. Okay, why do we have this? No idea at the moment. But what we can try to do is actually to use liquid. Let's load it. Module load liquid, and say that liquid pin minus C0. Let's have the process sticked on exactly on one core, and then what else? A.8 out. But this is not actually what I would like to do because I don't report the time. Do we have an improving performance? Here we have 91. Before we had 86, so not so much, but could be a fluctuation. But if I do now user bin time, yep, I have a, yeah, it looks like that something has changed, but I'm not pretty sure if it's just a fluctuation or not. Okay, so these are tools just to measure. So, well, again, a fluctuating 64, whatever. So it's let me see if I'm, so I tried 3 times and I got numbers around 0.40 for system time. Let me see if I get rid of the liquid, something is changing or not. No, so it was just a fluctuation. Okay. Yeah. So node perf is here. You can play a little bit around, whatever. Then what we have here is actually another exercise that I'm proposing you is actually, we propose is actually the following: to play with stream placing things in the wrong way. Okay. Michele was able to install numactl command. Okay, numactl is something more or less equivalent to liquid topology by means of this command, in which you see that the policy is default and then preferred node is current, and you have physical CPU bind. That is actually the way 72 CPU, and then we can bind to CPU 1, 1, 2, 0, 1, 2, 3, because we have 4 different CPUs. We can bind to node because we have 4 different nodes, sockets, and then we can in the memory we can bound to the memory in 4 different sockets. So what we can do is actually, the idea is actually that we can try to run stream in a way in which we bind the executable to the CPU 0, and we ask the executable to use memory relative to socket 0, socket 1, socket 2, and socket 3. Okay, so in this way what we can try to do is actually to access the wrong way the memory. Okay, again, we can ask the picture is always the same. We have the CPU, the socket, and the memory associated. Okay, then we have another CPU here. Okay, and the memory associated. And then we, by means of NumCTL, we can say, okay, run the code placing the executable here, but using this memory. These are for sure the wrong way to go, okay, because we are actually on the different memory. And then you can compare when the memory is associated to the right CPU, okay? And this is the experiment we ask to run our students, and they will always detect which is the penalty that you pay if you wrongly assign the memory to your process, to your project, to your process. So, in order to do that, okay, this is the command. Actually, the syntax should be this way now with the new stream is not available, stream OMP. Okay, what I'm doing here is actually that I'm CPU not bind on 0, and then I memory bind on the same socket. Okay, so I'm the optimal situation. Okay, and I'm running stream on this. Don't remember now how many stream LDD stream omp.x. This is a multi-threaded with MPI with GNU library GOMP. Export OMP num threads was actually to 1. Okay, and then I can run this way. Okay. So these are the numbers that I got. If I do this way, that is the wrong way to go. What do you see is actually that there is a decrease in performance. Let's do this one because this is actually quite funny. Not triad. Okay, so this is the triad operation, wrong way. Right way, 16. So quite a big difference, okay? I'm actually using one single core, okay? So I have one core that is running here, okay? And I'm reading the memory here. And then I read the memory directly here. So when I read the right way, so memory associated to the core, I got something like 16 gigabytes per second. That is good enough, let's say. And then when I go for that, performance drop. You can actually see if performance drop in a different way on different stuff.
It shouldn't.
It shouldn't because the
Only
distance,
were
exactly.
21,
Exactly.
instead of 10 or
Yeah.
I remember what.
Exactly. So you see that the numbers remains more or less constant here. Okay.
By the way, they stay also in the same ratio as the low number that we saw as the distance, 21 to 10. They are exactly approximately.
Yeah, 21 to 10 it should be that is actually a factor of 2. No?
Yes, not exactly,
But yeah, there is some correlation, let's say, of course, with the distance. What is actually funny is the following. Let's try copy. So this is the wrong way to go for copy. This is the wrong way to go for copy if we use 2. Okay, so 13, 14, 14, roughly speaking, okay, and then let's go on the same node, and that should be much better. What's happening here? Any guess? You are a little bit surprised. I'm surprised too, actually, because I should see different numbers. But I thought that this, let me just try an experiment, is actually something we can try, is actually this, because yesterday we played with stream. Did we play with stream yesterday? Yes, yeah, exactly. But we played in a different directory. And we are here, we were here, okay. And so now let's repeat LDD stream here, .x. This is a serial version. Let's try this. How much does it take?
The opposite.
Exactly the opposite. Any guess what is happening? Size. Size of the array we are actually copying and reading. The size is small in the first case. Here the size is larger. So, I don't understand why, for sure, because there is something behind that, but it actually the size plays a clear role. And so what actually, my guess is actually that in one case, on the small size, okay, for the copy, we are luckily exploiting better the caches. When we enlarge the size, okay, caches have no longer effect, okay, and in this way, we are actually measuring correctly the bandwidth between the RAM. We saw this only on copy, because on triad it was different. I mean, we have to check carefully on this, but on triad this was not actually the case. But on triad this could be explained in the term of the fact that triad does some operation. Okay, and so in this case, cache effect is actually there are floating point operation behind that, and so this cache effect can be a little bit thrown away. So this is my guess.
But yesterday we saw that the floating point operation was negligible compared with the
Sure, but still
memory resource
sure.
requirements.
Yeah, but this actually means in any case that you do something on the numbers. Here we have just a copy, so it means that read the data and come back. So it could be that actually you read the data and then you find that the same data in L3 cache. And so this is actually my possible explanation. I don't know if you have any comment on this. Gino, do you agree with this? Yes, this could be the other. What should we do in order to better understand this? Well, liquid perf, changing size, of course, and see if there is an effect, there is a particular size that actually drops this effect. So if this is true, decreasing the size will increase this effect. Okay, this effect, and then what we can do is actually to liquid perf control and see which kind of effect we have on the cache, and see if in one case the cache miss of level 3 are much less than the other. So that's the way I'm trying to explain you this behavior. Okay, in any case, the best just to avoid any trouble, let's look at the stream size that we have here. That is this. And let's now go in the other place. Yeah, it's 4 times less. No, ha ha ha. No. It's not able to resize the terminal in the right way. So I have to change it on a smaller terminal. Okay, now I can recompile it. Minus F open MP. Minus 3. Okay. Now it's coming back. Okay, so I recompile the code and now let's run again and see if it is true. No, seems still the one I saw, correct? It decreased a little bit, but still the other way around. So it's not just a matter of size. See, the wrong way, right way. That is actually the right way, but copy is still behaving weird enough. Let me just try one more thing. GCC stream dot c in -o stream dot strum.x GCC -o3. Let's get rid of stuff. Okay. This is correct. Copy. Wrong way. Right way. Still the other way around. So it's not the size. What else can be? LDD the same way. No, but it takes too much to be executed. So it should be some problem. I didn't change correctly the numbers. Ah. Let me see. Grep. Stream array size. Grep. Stream. Define. And then is the same number? Yes. No? It seems the same. No, I thought that I missed that 0 or something like that. Well, the program is not the same actually.
Different source code.
Yeah, it's different source code for sure. So it means that maybe there were something. Yeah. So the source code is completely different actually. So it could be that actually this explains a little bit the situation. Say again? Make? So this is actually the 5.10. So it's there is this line that tell me something that explain again. So version 5.10 increases the default array size from 2 million elements to 10 million elements in response to the increasing size of L3 caches. The new default size is large enough for caches up to 20 megabyte. So this means that this is actually the wrong behavior, correct? Because we are at, where are we? Okay. No, it should be the other way around, because I was telling you that. So this is the latest version that increases the size of the neon, and this is actually the version that give us the wrong behavior, no? Yeah, and then if I go this way, I guess. Yeah. Why this one? Let me just do this. Yeah. I was right in the sense that here we had a small array, okay, that fits into L3 cache, and so this was the effect. Now that we don't use anymore L3 cache, we see the right behavior. I was actually a little bit wrong comparing the two different code, the stream benchmark in the two different directories, because in the liquid directory stream was a little bit too old, and in this case it was also always working well, because I mean it was old and it was not actually optimized the same way this was optimized. So once you compare the same executable with the same source code with a larger array, we see that now we bypass the L3 cache effect, and now we have the right behavior. So copy is much better when you copy on the same memory. So what do we learn from that? Is actually that first, be sure that you provide the same stream executable everywhere, stream source code everywhere in your repo. This is my fault, of course, of that, but actually it was quite interesting to understand this kind of behavior. Again, it's something that nerd people like to do, but and so yeah.
Now, just to
Summarize.
summarize and to check if I have understood. Increasing the array size, you have totally excluded the L3 effects,
Exactly.
which were somewhere misleading you in checking the real throughput of the memory that you were reaching before.
Yeah, correct.
And now, with a big array size, having almost a completely excluded L3 effects, you see that with no
exactly. Because the point is actually that we have this L3 cache here. No? Because here is the L3 cache that we are using. Okay, and so the point is actually it's reading from here, but then it finds a lot of data here and start reading here.
Yes.
Once I have a larger array, this is completely bypassed and I'm actually reading and writing from the RAM.
What is
Yeah?
What is interesting is why, when we had the small array, the caching mechanism was acting better with the memory farther than in the case of the memory.
I mean, we have to check carefully, but my guess here is again, on Triad it was working correctly, because Triad is doing this kind of operation. A and B and C are all vector, no? LB plus C. And so here, 1, 2, 3 memory accesses, okay? 2 floating point operation. And so it could be that having 3 arrays, I'm actually mitigating. I'm actually bypassing easily the limit of my cache. So if I'm right in this explanation, I should see that this behavior is still there, not only for copy but also for scale. Because in scale we have just 2 array again. So let me see if it's true. That's actually quite interesting. But okay.
So it's the number of access to the memory that impact this.
Exactly, because I have just two arrays. In one case I have 2 arrays. In another case I have 3 arrays. So these 2 arrays are enough, and they are within the cache. They stay within the cache, even if they are large. So I'm benefiting from them. I have 3 arrays. Maybe they don't fit all in the cache, and so I have to go outside, and I don't see this. But what we have to see is actually, let's see this. Now I have to run on the small one. Still I have a stream on OMP here. Yeah, okay. And then I got copy, I got scale. I have to check scale. No, scale is behaving the right way. So my is not just the number of array is involved in the number of operation. So we have scale, triad, and then what is the other? Sum. No. Sum. No, it's not sum. Let me see. Add. Sorry. But you see here, the behavior is actually just on copy. Even add, even scale does behave the way it's supposed to behave, no? So this is the right way. And then we go the wrong way. The only opposite stuff is actually on copy. So my guess, I mean, it's for sure an L3 effect, but I don't know why. I don't know what is who is triggering this kind of behavior. I mean, because I thought that, I mean, it's actually the number of array, but it's not just the number of array. Probably the fact that the number of array, that is 2, and there are no floating point operation involved. And so maybe this is actually
It's not getting the data in the registry and then putting it back in the new position, because the copy is a very simple
Yeah, it's a very simple operation. So they just copy data, and then they say, okay, I don't have to do any kind of operation. So maybe I can. There is a prefetching mechanism that enter into it in the right way. I don't know.
Copy is the only one that doesn't have a floating point operation.
Exactly.
Right?
Exactly. That's actually so. For sure, there is some. The floating point operation is actually triggering the fact that the L3 cache effect is actually disappeared. Why this? Who knows? So that's actually the kind of stuff that you can you can get. Okay, so this is actually quite interesting. We learn. I mean, it's really nice. Of course, then there is another point that we can see, in which CPU node bind and mem bind, you can play the other way around. For instance, when we executed this small benchmark and this small test on the cluster at CISA, we realized that on some nodes it's not symmetric. We have two sockets, okay, and so you can assume that doing this operation or doing this operation is actually the same. From the logical point of view, should be the same. And actually, for many nodes, it's the same. But for some nodes, it's not the same. So we saw that in some cases, this was much worse than this. The effect
might be related with the physical timing of the RAM installed
exactly.
in the nodes.
Exactly. Maybe it's something related to this. We report it and they say, okay, we will check, then we never know what happened. But I mean, this is part of the general way. So you can see this kind of weird behavior of the number of sockets. Okay. Yeah. For the number of sockets in which maybe this is actually not correct. Okay. So you can look at the exercise. You can play with the exercise here. And then tomorrow, what I would like to do, well, now is actually 30. We are supposed to stop at 4:30, no? So if you wanna, I mean, now I will let you do a little bit of exercise by yourself, and if you wanna, I can stay here for a few more, 20 minutes till 5 p.m. if you have any question, if you wanna try things, and we can compare results and whatever. What else here? I have another small exercise AVX here you can play. That is actually, it's well documented, so you can try by yourself this to see the way AVX is working. Maybe minus G plus P. No. No, I was just looking at the fact that it's a very stupid example here in which we just do this operation, and this can be easily vectorized by the compiler. And so if you compile in the right way, you can have a great speed up. So here actually, if I compile this way, there is no optimization and no vectorization. If I ask him to compile, I got this kind of I can actually vectorize it. So and if I compile it minus 0 without any optimization, you see the difference, because actually the difference here is actually something like 9 seconds against 2.67, so it's quite well. What I would like to see is actually that when I vectorize, I should be able to use the floating point vector, this AVX, so this kind of stuff, but I see 0 here because AVX no optimize. No, I'm not actually reading correctly there. I'm not actually reading correctly this hardware counter actually. Let me see. No, this should be. Okay, so I think that everybody's actually disappeared. I can perfectly understand. Okay.